I have the honor to introduce a famous colleague of ours, Professor Gianni Royer-Carfagni. He is a director of graduate studies in industrial engineering at the University of Parma. He is also adjunct professor at the University of Houston in the United States, research associate and member of structural committee of the Italian Research Council, that's the CNR. And a delegate in the CEN TC 250 SC11, so that's the committee working on the future Eurocode. He has been also a member of the project team working on the structural glass Eurocode. He is an expert also at the Italian Ministry for Innovation of Structural Materials, and representative of Italian Superior Council of Public Works in Structural Committee UNI U73. Furthermore, he is Vice President of Glass Technologies Italian Association and Associate Editor of quite a lot of journals. And he is also involved in a new spin-off company of the University of Parma called Space Glass, if I'm not mistaken. Gianni, it's a long introduction, long CV, and we are looking forward to your presentation.
Thank you very much. I guess this is... Okay, the title of my presentation... Oh, thank you, Jan. Thank you for this nice introduction. The title of my presentation is Analytical Solution at Exact Effective Thickness for Multi-layer Laminated Glass Beams of Arbitrary Composition and an application to cantilevered balustrades. The first author is Ali Haidar. He's an excellent student, PhD student at the University of Parma. His scholarship has been supported by Maffei's Engineering, and then Alberto Consolaro, who is the director of the facade department at Maffei's, and Massimo Maffei, CEO and president of Maffei's Engineering. So I have an easy job now because Adam Nicic made a nice presentation this morning to introduce this argument. What are the motivations? First of all, simple models are certainly useful. And the problem is that the most used, like the Werfel-Benison model or the EET model, do not provide very accurate result when the geometry is highly asymmetric and also the loading. And there are more refined theories like conjugate beam, but they do not apply to any cases. And an analytical solution could also, apart from doing calculation, could also be used as a reference benchmark problem. So let us start with in a laminated beam, it is very important to take into account the shear deformation. And this is taken into account by the way in which the cross-section warps. And there are many levels, there are many models which provide different levels of accuracy. Like, for example, in the Timoshenko beam, just the cross-section remain plane. Then there are layer-wise theories which take into account the warping via smooth function. And in these cases, the shear strain is not constant, but it is varying along the cross-section. And zig-zag theories are very interesting for laminated glass because the warping is associated with non-regular function, which are piecewise linear, and this provides a shear strain which is piecewise constant in the cross-section. This is just an example of a zig-zag function and the possible warping of a cross-section that comes from this function. In the refined zig-zag theories, the shape of the zig-zag function is not arbitrary, but can be obtained from the continuity of the shear stress at the interface between the layers. And you can calculate what is the shape of the zigzag function from simple equilibrium, and it turns out to depend upon the ratio of the shear moduli of the various layers. What we have tried to do, we can simplify this model and under standard simplification. And the standard simplification is that you neglect the shear deformation in glass. So the glass ply become a simple Euler-Bernoulli beam. And on the other end, you let the bending stiffness of the interlayer go to 0. This implies that the role of the interlayer is simply to provide the shear coupling of the glass plies. And if you do this, you have a drastic simplification because the zigzag function becomes only a function of the geometry, the thickness of the interlayers, and in particular, the slope of the zigzag function becomes -1 on the glass, and depends on the various thickness of the interlayers in the other plies, but no dependence on the shear modulus. And from this is just an example of the resulting zigzag function. The important thing is that you can determine this from pure geometry, because the zigzag function must be 0 at the end, that is on the intradox and extradox. The slope is provided on the glass, and it is provided also in the region that are occupied by the interlayer. So extremely simple. Now, if you want to do a mechanical model, you have to define, for example, the strain energy and use a variational approach. And what we do here, we simply say, from the kinematical model, you can determine all the state of deformation of the beam. You can determine the strain. We just say that the glass ply are supposed to withstand bending stresses and axial stresses, whereas the interlayer is supposed to transfer only shear stresses to the glass ply. So it provides the shear coupling. And it is easy from this to calculate all this stuff. And the strain energy takes into account this thing, because the first part, it is the strain energy of a glass ply. The second part is the strain energy of the interlayers. So for what concerns the analytical numerical solution, you can add any kind of loading to this, any kind of boundary condition. You obtain via the variational approach, which are the field equation, the boundary conditions at the end, the matching condition for any type of geometry, for any type of end constraints. And the variational principle, the variational approach can also be implemented in a finite element method, very simple, very trivial to do that. But the nice thing is that the solution of this problem can be found in closed form. That is, you have a nice, lengthy, but exact expression when the bending moment in your structure is statically determined. So you can determine the bending moment from sole statics. You don't need to take into account the deformation of the beam. And if this is the case, and there are many examples in which you can determine the bending moment by sole statics, you can find out exact expression, if you wish, for the effective thickness for any kind of package, whatever is the composition of your bending, of your structure under bending. This is the finite element implementation. Of course, it is useful if you have a structure which is not statically determined. The variables are the axial displacement U0, the vertical displacement W0, its first derivative, and the function psi which takes into account what is the shearing of the various layers, because it is the function that multiplies the zig-zag function, and consequently the zig-zag function is the same at all cross-section, but the amount of shearing which is taken into account by the function psi may vary from section to section. So you can consider, for example, to take into account C1 continuity in W, you can consider Hermite polynomials, and you can consider a linear interpolation for what U0 and psi are concerned. This is an example of a convergence analysis for this simple problem. It is a simply supported beam. You can see here what is the laminated package. And you find out that you have a very nice convergence. Here, it seems that a large number of elements are needed, but if you are happy with 1% error, you can use 2-3 elements, 2-3 finite elements for all the beam. Now, if you want to have a very, very high approximation, you have to be a little more careful. And you have that the convergence in terms of displacement is very, very accurate and very straightforward. For what concerns the function psi, which takes into account the shearing, the convergence requires a little bit more of elements to obtain reasonable results. It should be interesting to notice that, for example, for psi is equal to 0 corresponds to the monolithic limit. And in the numerical approximation, it takes a little bit of time to obtain a zero function. On the other hand, when you are close to the layered limit, the function psi takes a certain value that takes into account how much the various plies are displaced one with respect to the other. The convergence in terms of W0 is very straightforward. The errors just with 2 or 3 elements it's very, very fast because in terms of displacement, the errors are usually very small because the deflection is only mildly influenced by other parameters. It is not the case for the state of stress. Now I show you just a simple application, the same one that Adam shows this morning. This is just an example. Of course, you can use the theory for whatever boundary condition you want. Here it is a cantilevered laminated glass balustrade. The important things in this model is that the shoe produces a constraint that can be interpreted by the static scheme on the right-hand side, in which you have a very, very short, simply supported beam with a long overhang. And another feature of the boundary condition is that in this kind of static scheme, you allow for the cross-sectional warping of the at the end of the beam. On the shoe, you can see in this picture that you have this relatively sliding of a glass ply. And this can be easily taken into account in the model by the boundary condition of a function psi. So in a variational term, you have just the natural boundary condition of psi at x is equal to 0. We have considered just 2 loads, which is uniformly distributed loads on the overhang and a concentration force F at the tip. The analytical solution is based on geometric descriptors. when you have the bending of a monolithic beam, you may have a moment of inertia of a cross-section. Here you have other function, which depends on the geometry, because they are correlated with the shape of a zig-zag function. They are simple second-order moment of area. The calculation are relatively simple when the solution, the cross-section is symmetric, but these are the quantities that enter in the differential equation. It's just a geometric description of a cross-section, which is slightly more complicated with respect to the simple bending of a beam, but can be easily calculated. So the governing equation are these. You have the boundary conditions and the interface condition on the central support. I'll not go to the detail, but just to say that if you change the boundary condition, if you say the constraint, you have other function to take into account. And the other thing is that this kind of equation can be integrated in closed form whenever your structure is statically determined. So whenever you can determine the bending moment from pure statics, you can find an analytic solution. So I just consider this simple problem with a symmetric cross-section because it is the simplest that I can imagine. These are the result of a state of stress at the extrados of this structure. The first graph is for the uniformly distributed load. The second is for the tip concentrated force F. I suggest to start from the second graph. You can see that the bending moment should be linear in the two parts because you are just concentrated forces. So if the beam was at a constant cross-section, you would expect that also the stress at the extrados would be linear. And you can see that it is linear in the layer, the limit, when the shear modulus of the interlayer. These are various graphs for different shear modulus of the interlayer. So the light blue curve corresponds to a very soft interlayer. You can see that it is linear, but if the stiffness of the interlayer becomes stronger, you have a deviation from the linear trend. So your beam behaves as if it was a beam with a variable cross-section, and the reason for this is that the shear coupling of the glass ply through the interlayer is different from section to section. And this is why you don't have the agreement of the shear stress with respect to the diagram of the bending moment. Then there are other features interesting, but that I don't have time to go into the detail. So this is, you can find the exact form of the effective thickness for this case. The expressions are very complicated, but you can use an Excel file. You do that once. You put it in your Excel file, and you have all the coefficients, which depends on the various elements. So let us look at the shape. You can see from these are the on the abscissa you have a stiffness on the interlayer, and on the y-axis you have the effective stiffness in terms of stress and deflection for the two load conditions that I have considered. To be noticed is that even if you have a very stiff interlayer means a stiffness of the order of 100 MPa. This is not sufficient to provide a monolithic limit. And the reason for that is the size effect of this beam. because you have a very short, simply supported beam, a very long overhang. You have a very high shearing in the neighborhood of a central support. So it's for a situation like this, is always very hard to reach the monolithic limit, and you have to do your calculation. For both, another nice thing is that for this particular case, the effective stiffness is only mildly affected by the load conditions. So more or less the two graphs are the same. This is a comparison with other methods. For example, we used a part of a special zig-zag function, which is this method, the Velvet-Benison, the EET, and the recently proposed conjugate beam ET. You can find that there is a perfect agreement between the conjugate beam ET, but as anticipated, you may have some problems when using the Velvet-Benison and the EET approach. So my final slide, what we have done, we have presented the special zigzag theory for multi-layer laminated beams that can be applied to any kind of laminated package with no problem. It provides exact solution when the structure is statically determined. We have proposed a paradigmatic example of a simply supported beam with a long cantilever overhang. We can derive, for whatever boundary condition, what is the exact expression for the stress and deflection effective thickness. We have verified that other ET methods are not accurate for this case. And when the beam is statically determined, the second order effect don't play a role because basically the geometric nonlinearities only slightly affect the deformation but not the state of stress. And these are the two papers in which you can find the theory. So I'm sorry I took a little bit of time to explain this model. I'd like to finish with a quote from Leonardo da Vinci, treatise on painting, and it is on the error of those who use practice without science. Those who fall in love with practice without knowledge are like the helmsman who enter a ship without a ruler of a compass, who is never certain where he is going. Practice must always be built upon a good theory. And in this case, I think that a theory, I don't know if it is good, but it is certainly a theory, that it is validated by calculation. I think it can provide, can save a lot of time and a lot of also of money in experiments. So I thank you for your attention.